Okay, hi everybody. Thanks for having me at another BigBrain Workshop. So today I'm going to talk to you about HIP Unfold version 2, improve robustness, detail, and minimize distortion. Oh, the podium is moving. Okay. So first of all, a little bit of background. So a lot of the ways that this gets talked about in the community, you might be forgiven for thinking that the hippocampus is subcortical. It's actually not. It's cortical. It's archicortex as opposed to neocortex. So I might say that it's an extension of the neocortex, but it's actually better to say that the neocortex is just a little extension of the hippocampus, which is the real show. So the way that I think about then hippocampal subfields is they're not really like nuclei like you might think of in the subcortex, but they're really more like parcels, just like we have in the neocortex. And so we did a lot of anatomical work studying the hippocampus, and basically we identified these anterior and posterior and proximal to distal endpoints. And this is like really critical. This basically allows us to create this coordinate system that spans across the hippocampus. And then HIP Unfold is this piece of software we developed that basically will automatically fit a surface between these endpoints. So it will keep a topologically continuous surface. And for those familiar with the hippocampus, you'll recognize this kind of curled up C shape. And so if you want to understand how that fits into the model, I've just taken a cross section here, and you can see that C shape that you usually see in a coronal view. So why would you do this? Why do you want to fit the hippocampus as a surface? So a lot of the same reasons that we've heard about in things like FreeSurfer and in Lindsay's talk as well. So we can do this surface registration, which basically helps us overcome all kinds of problems with doing volumetric registration. So most notably, we have these variable gyral and sulcal patterns that makes it very hard to come up with a deformation that will align different people. So the way we typically handle this in MRI then is we fit a surface to the brain and then inflate that to a sphere, and then we do this spherical registration to maximally align things like sulci. And that is amazing because then it gives us an equivalent surface across all subjects in any size cohort. And so then with that vertex equivalence, we can do things like nice statistics on a surface, and then we can also impose an atlas. For example, some of the atlases shown here. And yeah, we can do all kinds of mapping like you've kind of seen throughout the rest of this workshop as well. So we basically are doing this in the hippocampus. So you can see kind of an illustration at the top of how this is a hard problem volumetrically, so like people have different folding patterns. But what we have basically done over the last couple of years is we'll take two different hippocampi with different sorts of shapes and folding patterns, and we'll do this 2D unfolding. And then within that unfolding space, we can do something like we can do a 2D registration that's sort of equivalent to spherical registration on the neocortex. And so in the end then, we can go from, for example, Marcus Axer's 3D PLI dataset to this unfolded space, do some deformation in the unfolded space, and we have something that resembles BigBrain, and we can refold that back up into BigBrain. We actually just recently published this HippoMaps paper in Nature Methods that we're super excited about. Basically, we mapped out unfolded hippocampi in a lot of different really cool data sets. So BigBrain, the head brain, 3D PLI, Boris's precision neuroimaging 7T data, some intracranial EEG, just lots of really cool types of data there. So you can see they're all sort of summarized at the bottom there. And then we provide some tools for comparing different maps if you guys are interested in that. And as Boris alluded to, excuse me, in his talk, we're also working on an extension called Hippo Genes that we're quite excited about as well. And then another reason that you might want to unfold the hippocampus is that this can actually potentially have clinical use as well. So Conrad Weichstel and Mathilde Riepart also, they used Hip Unfold and extracted a bunch of features, and they showed this is very good for identifying TLE, even in MRI negative cases. So these, in a sense, you might say that Hip Unfold and their classifier they built on it is performing better than a radiologist in a lot of ways. So we're very excited about that as well. And so now today's goal. So we're actually going to move from version 1 to version 2. So we're going to make even further improvements on this. So first, I just wanted to mention, so this is a community effort. So we've had a lot of uptake in the community, which is amazing in no small way, thanks to everyone here. So we've had a lot of downloads, either from Docker or can be like on GitHub as well, people downloading the code directly. That I don't know how many there are, but we had 75 in the last 2 weeks. So I feel like a lot of people are probably using this. And over that, since we sort of first released this, we've had a lot of people giving us feedback, raising Git issues, emailing us. And so we've taken a lot of that community feedback, and we've been continuously improving this ever since. And so in a way, I guess I kind of wanted to acknowledge that. So these are some of the things that have gone into incrementing the HIP Unfold versions. But then I'm also going to talk about some major code restructuring that we've done to warrant this big jump up into version 2, the very special number. So first, a quick overview on how HIP Unfold version 2 works. So this is a little bit different from version 1, but I won't go into the subtleties. So you'll give it your input MRI image, and it will crop around the hippocampus for you, which you can see in this sort of footprint shape, or this is sometimes called PES hippocampi. We'll then use Nothing New UNet, the classic tool for classifying these different tissue types, including the SRLM laminae that look darker in MRI, depending on the contrast. And then we'll do this layerification. So this can be like an equipotential or an equivolumetric sort of model that basically spans from the inner to the outer surface. So in the neocortex, you can think of as white to peel surface. And then we'll draw a threshold somewhere along that. So this could be, this is called the level set surface. So we can draw a threshold at 0.5, so that would basically be halfway between the two, the inner and outer surface of the hippocampus. Maybe I'll just point to where yeah, that works. Okay, so then we have now a surface here, a level set surface. We can then work on unfolding that. So we identify these endpoints in the proximal to distal direction and also in the anterior to posterior direction. And from that, we basically have this 2D coordinate system that spans all of these different points in the hippocampus. So we can then draw a 2D map of all those vertices from that. And then in parallel, we also then take that surface and we compute a few things about it. So its curvature, its thickness, and its gyrification index. And this gives us then some data that we can show in this unfolded space. And so what we do then is register that data to a standard reference that we developed over the last couple of years from the multi-HIST7 data set that includes BigBrain, but also PLI and headbrain data and a few others. And then we can do that 2D registration. We can apply a standardized sort of subfield atlas, which can also be sort of modular. So if you want to input a different one, you can. And then altogether, you have basically this folded and unfolded surface with correspondence between all of your different subjects. And you can apply then a parcellation to subdivide that into subfields. So I won't go over all the changes that we made. Here are just like a few quick ones, and I'll maybe just note that like some of these have been introduced along the way. So I presented this, I guess it was 2 years ago, this unfolded registration that we did, especially for the 3D PLI to BigBrain alignment. And then some of these are actual major changes, but I'm not going to get into the nitty gritty. I just want to show a little bit the result. So on the top here, we have just some results from HIP Unfold, the latest version 1, and then some of the major overhaul that we see in version 2. So I'll just highlight the surface itself is more even, right? So there's, the vertices are more evenly spaced. So we went from having around 7,000 vertices to having around 8,000 vertices, and we made it so that they basically are a little bit more even. We solved some problems with so some of the steps involve things like interpolation, which always degrades the data a little bit. So that could sometimes lead to these funny outliers. So this is just 5 vertices along the dentate gyrus surface that create this huge ugly artifact. So instead of just removing those outliers, we've actually solved the problem at its core now, and we have no outliers being produced like that. And then removing those sort of lossy steps also allows us to fit almost perfectly like the center of this tissue in version 2 instead of in older versions where sometimes it could become a bit shifted. And then the final thing I'll mention is we changed the Laplace coordinate system just a little bit so that there's now more even, less distribution, or sorry, less, what's the word? less change in size between the folded and unfolded space. So you can kind of see this here on this qualitative example where all of these squares and these checkerboards should be about the same size. And now they're still not exactly the same size, but we should see that all of these squares are as close as possible in the average sort of hippocampal case to an even size. And so that was sort of a qualitative overview of some of the changes. We also have some quantification of this. So basically a few bar plots with numbers going up. This is always good to see. But I'll talk really quickly about how we got those numbers. So we basically took those XYZ coordinates from those surfaces and we compared them between 2 sessions of the same subject. So that's what we see along the diagonal, with the expectation that 2 sessions should produce identical results. And so we call this consistency. This is basically, how consistent is it between sessions? And the R values are extremely high, and they've gotten even, a tiny bit higher now with the new version. Then we also wanted to look at identifiability. So how unique is that surface to that individual compared to all other individuals? And so basically this would be the off diagonal. So this is these areas out here are between 2 different people. How different is that surface shape? And so we then treat identifiability like we basically take those off diagonals and just normalize by consistency. And so we get this plot here where you can see both at 3T and 7T, I guess I could have mentioned this earlier, the 3T and 7T both are showing this improvement. These are both significant differences with repeated measures t-tests. And then finally, the last thing we looked at is just mesh quality with sort of a standard way to look at this. It's called the scaled Jacobian, where basically 1 is a perfect score, 0 is very bad. It means like your shape doesn't make any sense, and you can actually have like below 0 as well. But in our case, we had very high scores here again, and you can see that they've gone up basically between version 1 and version 2. So yeah, basically that goal that we set out to achieve, we feel we hit it with these metrics. I also just want to highlight a few other things that have been integrated, not only in this, like the version 1 to version 2 jump, but within version 1, some of the changes we've made along the way. So always it uses this nothing new UNet model, which you can see like the original models are on the top row here, and they work very well for like high resolution or low resolution T1 or T2 weighted data. So they're quite robust. But we also had a few side projects looking at different kinds of data sets. So my colleague Brad Carrot basically developed a new model because this was failing in cases with severe atrophy. So he basically did a bunch of manual segmentation and correction to make this work in severe atrophy, and then also in the neonate here. So here where contrast can be very, very unclear, I guess. We're also, I'm basically out of time, so I'll just mention this super quickly, but we're developing a new model as well that's still work in progress, where we basically, we want to show very specific individual folds within the hippocampus. This was like, as Alan mentioned, something we discovered sort of in BigBrain, that this is so variable. And so we basically are trying to train a model using only extremely high resolution data derived from histology, where we have lots of folding. And we hope then that we can, create a bunch of synthetic MRI images at the bottom here and achieve even more. We're basically asking the model to hallucinate some folds into a hippocampus that's hard to see otherwise. So we're still testing that, and we'll see how it works. Some preliminary results show it's capturing some cool new folds, like this area here we call the vertical component of the uncus. So it's doing a good job there, and it at least is not inferior in terms of consistency and identifiability, but we're still working on this. So I hope that we can actually get it even higher still. And then there are a few technical things. So we've made this easier to access, easier to install. It runs faster. We sort of simplify the outputs a little bit just to things that people seem to really want to keep things lightweight. And yeah, this has really been driven by a lot of people in the community raising issues, asking questions, and sometimes even directly contributing code, which is awesome. I also want to highlight Ali Khan, who still finds time to code on this, which is amazing. With that, I'll thank everybody who has both developed this, supervised and discussed about it, or provided data directly. So thank you.